So last lecture, we had set the stage for effective field theories in general, but we did not discuss much about real life physics scenarios. So today let's start with the classic case of Fermi theory as an effective field theory. So the concept here is that the Fermi theory basically illustrates the effective field theory principles by integrating out the heavy fields, which include the W boson, the Z boson, the Higgs boson, and the top quark. So anything above the bottom mass, for instance, or anything above light particles in the light spectrum. So the degrees of freedom that we will have will only be because of these light particles which would remain. So basically we can even integrate out like particles heavier than the muons, for instance. So we can have muons, electrons, and their respective neutrinos. So what we would be trying to do in this first set of slides is to derive an effective Lagrangian for these particles. So let's consider the muon decay in the standard model. So what we have is this decay muon going to an electron antineutrino, and a muon neutrino. So the Feynman diagram is this, and I'll be discussing in two component spinor representation. So let's write down the charge current interaction like this. We have GL by root 2 nu mu bar sigma rho bar mu plus nu E bar sigma rho bar E, and the W boson, and we have a Hermitian conjugate. So this is the definition of the sigma vector. So and the sigma i's are the Pauli matrices. So now what we can do is, in order to give it the shape of an effective theory, we first need to write down the amplitude. We are not comparing it at the level of the Lagrangian, however we are comparing it at the level of the amplitude. So we write down the amplitude m is GL square by 2 x bar sigma bar x, then there is the propagator coming from the W boson, then the x bar sigma rho bar y. So here please note that we have 3 left-handed Weil spinors and 1 right-handed Weil spinor. So the one right-handed Weil spinor is coming from the antineutrino, the electron antineutrino, and all of the others are left-handed Weil spinor. So now if we consider the regime where the mass of the muon squared is greater than the momentum flow here and much less than the mass of the W boson, we can expand this propagator as 1 plus order of q squared by mw squared, and this minus of gl squared by 2mw squared comes in front. So now we are in the regime of low energies, as I discussed before. We are in the regime that q squared is much less than mu squared. So we can also write down an effective Lagrangian. So what are the possibilities of writing an effective Lagrangian which abide by the symmetry? So this is the only way we can write down the effective Lagrangian at dimension 6. So we see that mass dimension of the fermions are 3 by 2 each. So we have a dimension 6 Lagrangian, and we have written it down as c by lambda square, where c is the Wilson coefficient and lambda is the scale of new physics. So in order to match these two, so we are matching this amplitude with the amplitude that would come about from here. So we would see that we would be able to match the scale lambda with the mass of the W boson, and we will be able to match the Wilson coefficient as minus of GL squared by 2. So this effective field theory describes all charged current processes like muon decay, for instance, which I have discussed here, at energies much less than the scale of new physics, in this case the mass of the W boson. So at high energies, if we go to q squared much higher, then the EFT would not be valid and we will not have an effective nature to this interaction. So in the next lecture I'll more formally discuss with a few examples the validity of EFTs. So now before going to the standard model effective field theory, yes. So we haven't chosen lambda in this case. So like we don't know what the value of lambda is. It's just that we know that we have integrated out things from W mass onward. So lambda will correspond to W mass. Exactly. So this is mostly a top down approach rather than a bottom up approach. So before going to the standard model effective field theory, I would like to discuss a toy UV theory, which I would set the stage for how we have the concept of basis in an effective field theory. Like whenever we compute physical quantities in different bases, we should be getting the same physical answers. As well as something called matching, as we saw before. So I'll be discussing it through this toy example and then going to the standard model effective field theory. So let us describe a UV Lagrangian where we have a light scalar field phi with a mass of ml and a heavy field H with a mass of capital M. And we can write down the UV Lagrangian like this. We have a kinetic term for the light scalar, we have a mass term, and then we have a kinetic term for the heavy field, we have a mass term for the heavy field, we have a quartic term for the light degree of freedom, we have an interaction between the light and the heavy scalars, and we have another quartic interactions between them. So a Z2 symmetry, you can see here a reflection symmetry or a Z2 symmetry has been imposed. So when phi goes to minus phi, we have the exact same Lagrangian, so no odd powers of phi appear. And you can also see that I have not gone beyond h squared, even though I have written down phi to the power 4, but I have not written down anything about like h cube or h4. However, if you just draw a simple loop, you will be able to see that at loop level h cube and h4 terms can be generated.
So why you are keeping m mass of this lambda with the lambda 1?
What?
In the term of proportional to phi square h,
yes,
you have kept the m.
Yes.
Is there any necessity or to keep
this
the
one?
No, the second last term.
Second last one?
Second last.
Oh, this one.
Yeah.
Oh, so this is a trilinear interaction between two light scalars and one heavy scalar. It's a different dimensional reason. So it's a dimension. So the entire Lagrangian has to be dimension 4. Each scalar has mass dimension 1. So the mass has a dimension 1. So that's why it comes with a mass.
Okay.
Is that clear? Yeah.
Also have a phi squared del mu term, or that's by Lorentz?
Phi squared?
No, the probably del mu phi del mu h.
Del mu phi del mu h term we could also have had, but because I imposed this Z2 symmetry,
Individual.
which phi goes to minus phi, that's why I did not write that term. But
if I could like simultaneously flip the sign of phi and h, that term would have been.
That term would have been okay, yeah.
Yeah.
So it's not the most general Lagrangian. It's a Lagrangian, a toy Lagrangian. So now the EFT Lagrangian for yes.
That's a linear.
Yeah, I'll be discussing redefinition of fields. So here, yes, I can redefine exactly. Yeah. So now what we can say is that now this is our UV Lagrangian. We can also write down our EFT Lagrangian for energies much. Yes, please. Okay. So, okay, the question is like whether we will have more operators when we come from the top-down approach when compared with the bottom-up approach. So the answer is in general no, because from a top-down approach basically means that we assume that we know the UV theory. So when we integrate out the heavy fields, we get certain operators, but these operator coefficients now become functions of the original theory. From the bottom-up approach, all these operators are independent because I have no clue about my UV theory. So they are all independent. So there are more number of parameters in a bottom-up approach, but from a top-down approach, there are less number of parameters.
But there is more non-uniqueness.
There is more non-uniqueness, yeah.
So I don't think there is a trade-off.
It's not a trade-off because like we don't know the ultraviolet theory, so that's an assumption. So that's like, yeah, sure,
Ask a question.
sure. Does that answer your question, Vaibhav? Okay, yeah, yes. Yeah, from top down approach, the number of operators could be less actually. So if you have a, say you have a UV theory, right? You integrate out the heavy fields, you get certain gauge invariant operators. By gauge invariant I mean that whatever the theory is below that cutoff scale, it's invariant under that symmetry. So it will be invariant under that symmetry. However, when we go from bottom up, we will be able to write all possible gauge invariant terms, but from the top down we will only get a subset of them. Not all models will give you all the operators. Model number 1 will give you say n1 number of operators, model number 2 will give you n2 number of operators, and so on. So I don't know whether there exists a single UV model which generates all possible operators that can be written from in a gauge invariant manner. Okay, so now if the energy, so the regime that we are concerned, we are concerned at, if the energy is much less than the scale of new physics, the effective field theory Lagrangian.
When you integrate out this heavy field, yeah,
Yes.
There is no terms like related to this m square.
Exactly,
h
that's
square.
what I am going to discuss just here.
Okay.
Yeah. So when we integrate out the heavy physics, so when we write an EFT Lagrangian, as Bishwajit is saying, there should be no imprint of this H anymore. So when we write down the Lagrangian, the EFT Lagrangian, we see that we have the del mu phi squared term, we have the m squared phi squared term. Note here that I have not written it as ml squared phi squared, which I will come to. And then I have a phi to the power 4 term as well, but then I don't have any of these terms. I have a phi to the power 6 term. Why don't I have a phi to the power 5 term? That's because I started with a Z2 symmetry with phi goes to minus phi. So that is why this is the kind of effective Lagrangian that we will be having, but we don't yet know what the coefficients are. So these interactions are organized as an expansion in inverse powers of m. So here we see that these terms all have 1 over m to the power 0, then we have 1 over m to the power 2, then we have 1 over m to the power 4, and so on. These are all dimension 4 terms, so the Lagrangian already is at dimension 4, so we don't have any suppression with respect to m. However, any higher order term in mass dimension, they require suppression. Yes, please. So there is no reason per se, like here we are integrating, so our action is basically S is equal to integral d4x of Lagrangian. So that's, we have 4 space-time dimensions, so that's why. So that's how we write all of these operators, and each of these operators OD is of canonical dimension D, and operators only with even dimensions exist here. So note here that I had only written a dimension 6 term like phi to the power 6 by 6 factorial, right? However, why didn't I write these terms? Like I could have also have written terms like O6 hat is equal to box phi, where box is the D'Alembertian operator squared, then O6 tilde phi cube of box phi, O6 tilde prime phi squared of box phi squared, and O6 tilde double prime of phi squared del mu phi del mu phi. So I could have written all of these terms, but I didn't, I just wrote one term. So the reason is that we should be writing all gauge invariant terms which are possible. However, as we will see now, all of these terms will be made redundant. So this I leave as a homework exercise. It's very easy to do. Let's start with this operator, phi squared del mu phi del mu phi. If we utilize integration by parts, we will be getting phi cube box phi with a factor, and if we integrate by parts phi squared box phi squared, we will be getting again phi cube box phi. So, these two operators can be traded by O6 tilde, they are not independent operators. So, now field redefinitions and their equivalence. Any questions? No. So, now we can use the classical equations of motions for this system, and we can try to eliminate either or both the O6 hat and the O6 tilde. So, in favor of the operators that we already have. Now, if we shift the Lagrangian by terms which are proportional to the equations of motion, it will not affect the S matrix. So, this is the equivalence theorem per se. So, the equivalence theorem basically is that if we have a transformation of the field phi, which is a good transformation, by good I mean that it is a local transformation, it is an invariant transformation, then what we will see finally is that the S matrix calculation will not change. However, if we have a non-local transformation, the calculation could change, so it would be called a bad transformation. So, if we have the so called good transformation, so I will give you an example of a good transformation. So, if we say have a transformation like phi goes to phi prime is equal to plus phi plus epsilon phi cube. So, this is going to be a good transformation. However, if we have something like phi goes to phi prime is equal to phi plus epsilon integral of d cube x some then this is not going to be a good transformation. Sorry, d4 over d4y. So, it is not going to be a good transformation, and we will not be able to get the same S matrix. So, this is called the equivalence theorem, and I would like you to have a look in details about the equivalence theorem. So, note here that, can we please switch off the light? This is non-local, this one. So, what we see here is that here in none of the terms we have any box, we do not have any D'Alembertian operator in any of these terms. However, we can actually go to from the box unboxed basis to a box basis by just doing some field redefinitions. So, for example, if we go from the unboxed basis to the box basis, we just need to redefine the field as this, which you can see is similar to this. So, this is phi goes to phi plus a coefficient phi cube. So, this epsilon is small. Here again we have a small coefficient because m is a large quantity.
When you say that we can use classical equations of motion to eliminate, these classical equations of motion are derived from the new Lagrangian or the old Lagrangian?
From the old Lagrangian. So, L as a function of phi and del mu phi, if we vary the phi field by an infinitesimal amount by phi goes to phi plus delta phi, then we will be able to see the change in the action, and from there we derive the Euler-Lagrange equations, and from there we get the classical equations of motion.
Okay, and the second question is that thing independent from doing integration by parts and then removing these terms?
It includes the integration by parts. So, when we actually write down, so what will be the terms? So, the terms will be so we have our Lagrangian phi del mu phi. Now, what we can do is we will have basically delta S is equal to del L del phi delta phi. So, now phi goes to phi plus delta phi plus del L del of del mu phi delta of del mu phi. So, we can actually write delta of del mu phi is equal to del mu of delta phi, and using here we can actually do an integration of by parts of this term. We get a boundary term and then we get the other term. So, basically we finally get something like so this will be equals 0, and so for an arbitrary delta phi this whole term would be 0. Sorry, here, right? Oh, right. Oh, sorry. So, what we can do is that if we transform the field, so we will be able to see this explicitly. So, if we redefine the field, we will be able to see this explicitly. So, now what we do is that this is our equation of motion which we get from the Euler-Lagrange equation, box phi plus m squared phi plus c4 by 6 phi squared is equal to some order m to the power minus 2. So, this is the classical equation of motion for phi. So, we ignore any term higher than order 1 by m squared or even higher. So, now what we do is that here we have box phi and we had an operator box phi squared. So, if we square this term, we will be able to see that we are able to trade off the box phi squared already directly. Yes. Yes. Yeah. Oh, this is from the EFT Lagrangian. We can see explicitly this C4 by 6. Yeah, this is from the EFT Lagrangian. And if we multiply this term by phi cube, we will see that we will be able to trade off phi cube box phi in favor of phi to the power 4 and phi to the power 6, and there will be an order m to the power minus 4 term. So, we have been able to successfully remove all of these 4 operators in favor of phi to the power 4 and phi to the power 6. Is this clear to everyone? Yeah. So, alternatively, what we could have done is we could have written down the Lagrangian as these terms which are similar, which are the same, del mu phi squared minus m squared phi squared. We have C4 tilde phi to the power 4 by 4 factorial. Note here that here I wrote C4, here I am writing C4 tilde, and here I am writing C6 tilde, and here instead of writing phi to the power 6, I have traded this off by phi cube box phi, and this transformation, this field redefinition takes me from one Lagrangian to the other.
So in the first equation, you have removed the terms of the order of m to the power minus 2.
Yes.
Why it is so? So in the Lagrangian, you have kept the term.
Yes.
Proportional to the m.
Yes, I could have just written that. There is no problem. So it's just that I haven't written explicitly the term 1 by m squared. It's there. You can just plug it in. There is no harm in.
You are not ignoring that.
I am not ignoring it. It's just that I have just ignored from writing here, but it's there. It's there in the calculation. It will not give you any extra term other than phi to the power 4 and phi to the power 6. Yes. Can someone give him the mic, please?
So we are trying to understand that when you have written down the Lagrangian in terms of phi 4 and phi 6, why can't we include those other, like why those other operators are redundant?
Yeah.
But like initially we are adding those operators in the Lagrangian.
Yeah.
EFT, and then we are trying to show that they will just give back us the phi 4 and phi 6 interactions.
Exactly. So you write all possible gauge invariant terms, whichever is allowed, and then you see which of these terms are either becoming redundant either by equations of motion, by integration by parts. Something we'll see in the when we discuss the SMEFT, the Fiat's transformations, So these are the reasons. In these ways, we will be able to get rid of the redundant operators.
Yeah, but my question is, if we have included those redundant operators in the
Yeah.
Lagrangian, why are we still using the old Lagrangian to derive the equations of motion?
So, in this case I did not include them. In this case I had only kept 5 to the power 6 by 6 factorial. I have not included them in the Lagrangian. Now I take all of these operators. So I had written this Lagrangian, and now you come and tell me, oh, but these terms could also have been there. So now I tell you that these terms won't be there because of this reason. That's it.
Yeah.
So if you had written all of these terms to start with, the coefficients of each of these would have been changed. So we would have had C6 1 prime, C6 2 prime, C6 3 prime, C6 4 prime, and so on. That's about it. But all of these terms would combine to give this. So, but in the original Lagrangian I did not write those terms. What, where?
Is this true to any order that the EFT does not have any derivative couplings? Because all of them can be either field defined away or go to.
In this case, yes. Not always.
Yeah, in this case.
In this case, all derivative couplings are just washed away. Yeah. Yeah.
So conversely, can we also say that this C6 can be rewritten in terms of these C4 tilde, C6 tilde? I mean, does it have?
Yes. I was just
Okay, sorry, I missed it.
coming here. Yeah. So now so what I wanted to describe here is that here we wrote the EFT Lagrangian in a certain basis. So this is where the concept of basis comes into the picture. So here the basis is basically what we call the unboxed basis, and here we go to the boxed basis. So the parameters are different, the C4 tilde, the C6 tilde, these are different, but whatever physics calculations we do with either of these bases, the result should be coming to be the same. The box nomenclature it's very like it's not a very fancy way of saying it, because there's a box. This basis I named it as box basis. There is no box, it's the unboxed basis. It's nothing fancy between it. So now coming to Juhi's question, we can relate the coefficients with the Wilson coefficients between these two bases, and we can actually, this is called the translation between bases, and we can write it as this. So you can try and do this as a homework exercise. So you have all the ingredients, you just need to plug in and see how these bases actually match with each other. So you have the field.
Sorry, I have. So you said S matrix elements are invariant under these three definitions?
Yes, but there will be a Jacobian which would be different under these field redefinitions, but like when we integrate it out, like all the it shouldn't be there.
And is it just the S matrix elements or also some more general objects?
All the observables that we see, all the physics observables, like when we talk about in the standard model EFT, when we take, like, say for instance the Warsaw basis or the Silch basis or the Higgs basis, whichever basis we choose, the final cross section that we compute for a process, they are always going to be invariant. It's going to be a basis independent quantity. Does that answer? Yeah. The partition function will get a new field, so like the new field definition. So the partition function will not be invariant.
But the partition function is a function of the external currents. There are no fields there.
So the partition function, just let me think for a moment. So the partition function, if I redefine my field, the partition function would look different. That's about it.
It can't.
Let me think for a moment.
Z of j.
So Z of j only is the external source. That we are not changing the external source. We are just redefining the field. So the partition function should remain exactly the same. It's an on-shell S matrix. So if we are not dealing with on-shell S matrices, then we won't be able to make this statement. So as I said before, these are well-behaved field redefinitions.
Excuse me.
Right. So, for a particular effective theory,
Yes.
do we know that what are the number of bases will be coming, or like
It's infinite. For any effective theory, the number of bases that we'll have is an infinite number of bases. But we won't know what all of these bases are. We only use some bases which are pragmatic to use. So in standard model EFT there will be infinite number of bases. But
so
yeah.
it can happen like somebody for that particular theory can have some other basis.
Yes.
And can we map one?
Yes.
Like.
So we'll have, so just like here I showed translation between two bases, we'll be able to map any bases. So all bases can be translated and mapped onto each other.
Okay. Thank you.
Yeah. So I'll be discussing, so one thing which I'm going a bit ahead of myself is that if we talk to experimentalists for instance, then usually, Shantanda is laughing. So usually we don't talk about the various bases. So it's not a good idea to talk with experimentalists in terms of bases. What we talk to experimentalists are in terms of observables. And they understand what these physical observables are. When they give us the information about these observables, we can map them onto any basis of our choice. And between theorists, we can just translate bases. And that's a task that we can do using the equations of motion and all the other things that I discussed.
Also, when you calculate the observables, does it matter whether you are the box, example?
It doesn't matter at all. It doesn't matter at all. Yeah, exactly, exactly. So now I'll be discussing tree level matching, and if time permits next day I'll be discussing loop level matching as well for a very simple scenario. So at tree level, let's again take this same example. I've written down the UV Lagrangian and the EFT Lagrangian once more. So you can see here that the UV Lagrangian has phi to the power 4 and this interaction term phi squared h and then phi squared h squared, whereas for the EFT Lagrangian we have phi to the power 4, phi to the power 6 and so on. So we can identify the matching coefficient. So we can identify ml squared with m squared. So remember here I did not write it as ml squared because a priori I did not know whether there will be some absorption of a part of ml into some other quantity. So I had kept it generic, I did not write it as ml squared, but now I see that it didn't affect the mass squared term. So we can identify m squared as ml squared. Now let us consider a 2 to 2 scattering process, which is the easiest scattering process that one can think about. So a phi phi to a phi phi scattering. So the contributions would come about from this 4-point function. So now we are calculating in the UV theory. So this would come about from this 4-point function and it would come about from these 3-point functions. So this phi phi capital H, phi phi capital H. So each of these vertices come from this lambda 1. So we will have here a term which is proportional to lambda 0, which comes from this 4-point interaction, and then we will have all these 3 terms. So we will have an S channel, a T channel and a U channel. So these are the S, the T and the U are the Mandelstam variables, as you know very well. So S is basically when we have the momenta as P1, P2, P3 and P4. S is basically P1 plus P2 squared, T is P1 minus P3 squared and U is P1 minus P4 squared. So we can write down the amplitude of the 4-dimensional, the mass dimension 4 UV scenario as lambda 0, lambda 1 squared m squared. So see here that the 4 factorial goes away because these are identical particles. So I am not doing the full calculation here, but you can see how this comes about, and we have S minus m squared, T minus m squared and U minus m squared. Now we if we are in the regime where S, T and U, which are basically combinations of these momenta, to be much smaller than the scale of new physics, then we can write down, we can expand this. So what we can do is we can flip the sign here, we can take plus lambda 1 squared m squared, so it would become m squared minus S, m squared minus T and m squared minus U. I take out m squared from here, so it would be 1 minus S by m squared, 1 minus T by m squared, 1 minus U by m squared, and I expand this and I get through binomial expansion a 3 term from here, 1 plus 1 plus 1, and then we also have these S plus T plus U. And S plus T plus U, you have done it in your particle physics course, it's 4 ml squared. So this is basically my amplitude coming from here. Now if I go to the effective theory, what I have is only this blob, that's about it, this effective vertex. So when I compute it, this M4 EFT is just going to be minus C4. So remember, in the first lecture I said that we cannot just put the JH is equal to 0. So we will have a difference between the EFT, MEFT4 and MUV4, and that difference would be this O m to the power minus 2. So it would be a difference because of these additional operators. So what we can do is we can now map both of these. This we had already mapped, and C4 from this expression we will get C4 is equal to lambda 0 minus 3 lambda 1 squared minus of 4 lambda ml squared lambda 1 squared by m squared. So this is my matching, this is how we do matching between two theories. Yes, please.
The dropping out of the momentum variables was accidental, and hence the C4 just is a number and does not have derivative interactions.
Exactly, it doesn't have any derivative in interactions. It's a constant.
Yeah. So if you just kept going to higher order within the tree level itself,
yeah,
you still don't have any STU. It's all
I don't have, no. Yeah. So all of these Wilson coefficients would be constants. So they would not be constants actually. That should bring me to RG evolution of these Wilson coefficients, which I'll be discussing in the next class. But for now, at a fixed energy scale, they are not functions of momenta. So now this again I leave for you to do. I did this calculation. It's easy. It will take you 15-20 minutes. So if you do a 6-point calculation, you would get C6 as 45 lambda squared lambda 2 minus this. So please try this out. So here we did this calculation in the unboxed spaces. So I would urge you all to try this calculation in the box spaces. So mind you, for the box spaces, nothing changes for the C4 term, because in the box spaces the C4 term was exactly the same. Only the C6 term had changed. So if you are trying this, like this would be, if you are interested, this would be a good practice. C6 versus C6 tilde, and convince yourselves that it would map that relation. So what about matching at one loop? So this is the lecture for next day, and I'll be discussing it then. So now, before I go on to the standard model EFT, I would like to say that we know that standard model is a really beautiful theory, and it's a theory of quarks and leptons which interact via all these forces, the strong, weak and electromagnetic, and it is valid up to very, very high energies because it has passed countless experimental tests. However, it has limitations. For instance, experimental observations, gravitational observations of dark matter, then we have observations of neutrino masses from neutrino experiments, baryon asymmetry, cosmic inflation, these all point to non-standard model scenarios. There are also theoretical issues like the strong CP problem, flavor hierarchies, unification and so on. So this basically says that standard model, even though it's a beautiful theory, it's not the last theory that we would hope for. So
why do you say the standard model is not enough for baryon matter antimatter asymmetry?
You do not get enough CP violation in the standard model without the introduction of anything additional to, so if you look into the calculations, you will not be able to generate enough CP violation from any of the sectors.
But that's probably an equilibrium expectation, right? I mean,
yeah, but like it will still, it's still way under what we predict. So here, before delving to standard model EFT, I would like to tell you about why we want to do EFTs when it comes to a beyond standard model rather than studying like model after model after model. So here I have named it model theistic versus model agnostic approaches. So this is a cartoon taken from Tim Tate. So these are many theories of dark matter, of which some popular ones are sterile neutrinos, extra dimensions, supersymmetry and so on. So there are so many different kinds of models which could give rise to dark matter candidates. So there are and since 2012, we have had no real direct hints towards any new physics, which explains all of these observations that I talked about. Now, I discussed it the last day, so whenever we discuss a model, all of these models come with additional baggage. So unless we are able to discern the complete model, we will never be able to say, okay, this is my correct model. So there is no consensus between theorists. Even in one theorist's head, there is no consensus, because we all work with many models. We are not sure about what model is the right model. So the next point is that, is new physics hiding somewhere that we are obviously missing? So it could be that new physics is just outside the reach of the LHC. So that's one way to look at it. But then how outside? We don't know. We don't have an answer to that question. So then the next question is, if there is some new physics, are the interactions with the standard model particles, if at all, otherwise it would be a nightmare scenario if there is no interaction at all, are the interactions extremely feeble? So if the interactions are extremely feeble, then we could hope that with more and more collection of data, we would have enough luminosity such that we might be able to see this new physics. But we don't know that yet. And the next question is, are the theoretical and experimental precisions not good enough? Yes.
Just a naive question, like if I think about the standard model EFT,
yes.
So the field content will be the same as the standard model, and how it is going to cover the dark matter?
Okay, so dark matter, the standard model EFT will not cover dark matter. So for that we need beyond standard model EFT. So we need the introduction of a dark matter particle. It's just that it simplifies and writes down the operators in terms of, like, so we can have a lot of dark matter models with various kinds of properties. We can actually plug all of these properties inside some dark matter EFT, that's about it. But we need to plug in dark matter. Even before going to dark matter, I'll come to it, even if we talk about neutrinos, if we talk about, if our neutrinos are Dirac particles, standard model EFT is not a good way to formulate it. It will not be enough. Yes.
I mean, it's easy to see this from your classical example that you started out with. Given an observation of few terms and the experimental error bar, you could write infinite number of UV completion.
Yes.
So what is the objective goal of top-down approach then? If there are infinite number of them,
yes,
you can always say,
yeah,
whatever level of experiment you do, that there will be some error bar,
yeah,
and you can fit in infinite number of models in there.
Exactly. So in that way, probably we'll never find the correct UV model.
Correct. I think it's unscientific.
It's unscientific because but the thing is that we probably will find something which describes all of the observations we have. But then again, if there's some new observations tomorrow, this new model, this new UV model that we have toiled for so long might not be enough. Then some additional.
There is no new model. There is always an infinite number of model which will explain the existing observation results.
So what I said is that it could be an infinite number of models. Of course, it could be an infinite number of models, but again,
very large.
Theorists prefer simplicity. So they would try and pick the simplest of. So for example,
that simplicity is just a bias.
It's a bias, of course. I completely agree. So for example, a new physics model could just have an additional scalar, or it could have 5 additional scalars. So what theorists would try to see is that, like, if a model with 1 additional scalar describes whatever observations that I have, it's a good enough model. But that does not rule out all these other ones. So we will never be that's the thing. Like, we will never be able to fully rule out.
I think it's in principle problematic.
Exactly. It's in principle the whole idea of like finding that golden UV model is not something that we'll ever find, because there's no one unique one in the end. So yeah, so the next point was that, are the theory and experimental precisions not good enough? So what by this I mean that theoretical precisions come in the form of higher order corrections, in EFTs, which I will be discussing the next day, theory precisions can come from something called operator truncation. So, whether I am truncating my EFT at a certain mass dimension, by truncating the EFT at a certain mass dimension, what kind of error is coming in. Then whether or not we are taking higher order corrections like QCD or electroweak corrections, whether or not we are taking RG evolution of the Wilson coefficients. So, these are all the theoretical bias, theoretical uncertainties that could be the reason why we have not seen new physics till now, and experimental precision as well. As we discussed, Shanmoy discussed, we still are in the regime when experimental precision is not as good enough, like not at the level of a % or lower, that we are able to discern very, very small deviations. So, we have not come to that scenario yet. So, instead of that, what we can do is that we can take some BSM models at some scale lambda, say, and we integrate out the heavy fields and we get SMEFT from a top down approach. We could have also gone from the bottom up approach. So, EFT approach and motivation for SMEFT. So, new particles which, like beyond the standard model, new particles and interactions, these are actually motivated by no direct or indirect signs for collider signals or any other signals. So, we have not seen any direct or indirect signs. Signs, yes, but absolute discoveries, no. So, there are hints of new physics here and there, but we have not yet reached statistical significance for any of those. So, in the EFT scenario, as I have been discussing over and over, new particles, these are going to be much heavier than the weak scale in the standard model EFT, and they can be integrated out, and their effects are then going to be captured by adding higher dimensional operators to the standard model. So, the SMEFT actually extends the dimension 4 standard model by including all possible gauge invariant operators if we write it in the bottom up approach from the standard model fields with the same SU3C, SU2L, U1Y symmetry, and they are organized in this series expansion. We have the standard model Lagrangian piece, we have a dimension 5 piece where 1 by lambda and operator dimension 5, because it has mass dimension 5 we need a suppression by a mass scale. Then we have dimension 6 operators suppressed by lambda squared, then dimension 7 operators, and so on. This series continues. So, this expansion is only valid when the vacuum expectation value is much smaller than lambda, where this lambda represents the mass scale. So, next time I will be discussing a scenario when we will not be able to describe the EFT as a linear sum like this. So, this we will be calling the HEFT or the Higgs effective field theory, and it will be in principle different from the SMEFT. They are all Wilson, these are the Wilson coefficients. These are bottom up, yes. So, because of the Wilson flow, yeah, but it is used for bottom up as well. So, let us take the first situation, dimension 5 operator. So, we will see that there is a unique dimension 5 operator in standard model EFT, like barring the flavor. So, if we have, so we can have, if we assume that there are operators for different flavors, like, so here I have written down this operator O5ij, where ij are basically the flavor indices, and these are, this is the operator epsilon ij hi lij, epsilon ij hi ljj. So, this I and j, these are the SU2 indices, and the I and the j are the flavor indices, and this epsilon ij is the antisymmetric tensor. So, here we see this is the effective vertex that we can write. So, why is this dimension 5? We have dimension 3 by 2, mass dimension 3 by 2 for the leptons, the lepton doublets, and we have mass dimension 1 per Higgs. So, that is why we have dimension 5. So, yes, sorry.
Here L is a Dirac fermion or Wien?
So, here L is basically, so it's not Dirac. So, so here I will be talking about Majorana neutrinos only.
Okay, so it's like while only.
Yeah, if written in two component notation, it would be while.
If I ask like why don't you contract it using sigma tools?
Yeah.
Or it should be doable, right?
Yes, it should be doable. So that we can do that using Fiat's identities. Sorry, you have a question? Shanmai's comment. Shanmai said that we could have written it in terms of some sigmas as well, like the Pauli matrices.
Inserted a sigma mu here and sigma mu there as
If
well.
we create a lepton bilinear, fermion bilinear, we will be able to write it as, we will be able to use the Fiat's identity, and then we can have those terms.
No, sigma bar mu has an SU to R index. It's the sigma mu has it.
Yes.
Yeah. So you can make one of them as left-handed, one of them as right-handed, and insert a sigma inside. I mean, just as Shankha said, like the Fiat's identity games you play. So this is not a unique representation of the dimension 5 operator. Yeah.
So we can always use Fiat's.
Yeah.
So this operator, as we will see, will violate the lepton number as well as B minus L. So this will lead to Majorana masses. So it's not a Dirac mass, it's not a Dirac neutrino. So after imposing the wave, after the spontaneous symmetry breaking, this operator would generate a neutrino mass term like this. So we will have a 1 over lambda C5 ij. This would give rise to V squared over 2 lambda C5 ij nu I nu j. So it's a Majorana mass term. So the mass m squared is identified with this. However, from neutrino oscillation experiments, we know that the masses of the neutrinos are less than electron volts, and at least one of them is heavier than 0.06 electron volt. So what we deduce from here is that the lambda by C to C5 should be greater than 10 to the power 15 GeV. So Vaibhav has a question. Yeah.
So so I have a very naive question.
Yeah.
So the thing is like you just said in the last slide ki if it seems to me ki if we want to probe higher heavier like in top bottom approach, where we integrate out all the heavier fields. So as like heavier and heavier mass we want to probe, and higher, and then you have to add higher and higher dimensional operator to add to your
No, it's not that. Like a single mass scale, a single heavy mass scale can generate operator at many orders. It can generate operator at dimension 6, it can generate operator at dimension 8, and so on.
Do we have to take in account all the operators? Because if we don't take account, we don't consider them, then their effect will be in the lower dimensional operators, right? Like.
So just to clarify, I have my theory here. I have my standard model below here, which is the vacuum expectation value, and this is my heavy scale lambda. So all new physics, can you please switch this on? So all new physics lie above this cutoff scale lambda. So the integrating out is happening at this scale. So the integrating out of the new physics is happening at this scale, and these operators O1, O2 and so on, O3, they are valid in this regime. So they will have different dimensions depending on how I integrate out the fields. Whether I integrate out the fields at leading order, whether I integrate out the field at next to leading order, whether I integrate out the fields at next to leading order, whether I include all kinds of heavy and light mixing in the loops, that would give me different kinds of operators at different dimensions. As we will see later on, that some of the operators can only be generated at loop level, and not at tree level. So we will see that there exists some operators which can only be generated at loop level and so on. So this is the only thing that I am talking about. So it has nothing to do with top down or bottom up. So if we are going from a bottom up approach, we cannot throw out any operator, because if we do, we are violating gauge invariance. From a top down approach, if we are throwing away any operator which comes about, we are just biasing the results. So we should not throw out any operators.
Thank you.
There is no integration out, it's just that we write all possible gauge invariant operators. These are all fundamental parameters. Okay. So here I said that like the neutrino masses are very, very small. Sorry. The neutrino masses are extremely small, and what we see is that the lambda by C5 is greater than 10 to the power 15. So usually the kind of coupling strengths that we are used to see in standard model are kind of like weak couplings or somewhat strong couplings. So if the neutrino coupling is kind of a weak coupling, so C5 would be of the order of 1 only or less than 1. So that means that lambda has to be greater than this 10 to the power 15. So it's a huge scale.
So the 5-dimensional operator that you have written in the first line.
Yeah.
So that is keeping in the mind that we want to discuss. So we wish to calculate this neutrino mass, or there is any so that written in the within the keeping in mind some expectation about some physical processes, right? So
no, it just like it's a lepton number violating process, operator, and so this is the unique operator that comes about in dimension 5. There are no other operators in dimension 5, no other structure. This is the unique structure that comes at dimension 5.
Okay.
In low energy field theory, you get more operators at dimension 5, but in standard model effective field theory, this is the only structure that you get, which is called the Weinberg operator.
So, like this term also can explain the mixing, neutrino mixing.
This term is not exactly, because it can actually discuss, yeah, because there are two flavors, two flavor indices, so it can, so there will be off diagonal terms as well.
So let's say if we consider the giving bound from the mixing, so whatever the measurement has been done, and how do you incorporate these two bound, and they are lying this 10 to the 15 G.
So we have, what we have are delta M12 squared, delta M23 squared, and so on. So we use those values to, so we have M1 squared minus M2 squared, mod of M1 squared minus M2 squared, mod of M1 squared minus M3 squared, and so on. So these are ballpark numbers. So these are order of estimates. These are not exact numbers here.
How did you estimate that number?
This 10 to the power 15. So I did it, so you plug in V as 246, and so you map this to basically V squared by 2 lambda. So this is like a mass. So you write the mass around 0.06 eV, and you write V as 246 GeV squared. So and
okay, so essentially you get the mass term from the
this
Weinberg operator
from this
and then,
bound,
and
exactly.
then match it with the bound.
Exactly, that's about it. So see here that I have been saying that this cutoff scale lambda from this neutrino mass is very, very large, because if we assume a weak like coupling, this lambda by C5 greater than 10 to the power 15 would translate to lambda greater than 10 to the power 15. So it's a huge number. So this implies that dimension 5 effects are extremely tiny, and except in neutrino oscillations where we do see some observables. However, we will be seeing that dimension 6 operators, they provide leading order effects at the weak scale. So what is EFT as a framework? So it is a technique, and it's widely applied across various fields in particle physics, and they basically provide a systematic expansion of the Lagrangian, and we organize the operators according to symmetry and energy scale. So when the UV completion is known, so for instance in the Fermi case, or in the chiral perturbation theory case, or in the Einstein-Hilbert gravity case, so the EFT Wilson coefficients may be calculable in the Fermi and the Einstein-Hilbert case, or not in the chiral perturbation case. So in the next class I might be discussing chiral perturbation a bit more, why it's not calculable because of non-perturbative effects, just to give you a hint, and they are calculable coefficients may appear at tree level or only at loop level.
Why are you calling Einstein-Hilbert UV completable? What are you thinking of, like string theory?
So yeah, I don't know the exact details, but I just know the Lagrangian, that's about it. So the gravitons come as the modes. Yes. So when by that I mean is that, say for example, for the Fermi theory, which is at the muon mass scale, my UV completion is the standard model, basically. That's what I mean by it's known. But if I come to your philosophy, it's still not known. So yeah.
That's fine, but yeah,
that is what
the same question about Einstein.
That is what I meant. So when UV completion is not known, like the bottom of SMEFT, the degrees of freedom, they may be fundamental, they could be emergent. This emergent terms comes about because in chiral perturbation theory we have non-perturbative terms. So because we write it in terms of the pions, which themselves are not fundamental particles, but they are made up of constituents like quarks and gluons, or they are completely unknown. So this benefits of SMAFT, it's basically there's nothing here, but there are additional applications. I don't think I'll be able to discuss these, but there are many kinds of EFT. So I'll be mostly focusing on standard model EFT and Higgs EFT, but there could be heavy quark effective theory where we have one heavy quark like the B mesons. We can have subcollinear effective theory for QCD collisions, or we can also have NRQED. We can also have like non-relativistic effective field theory for dark matter. So there are many kinds of effective field theory at play. So now something quite interesting is that although the standard model is successful, it doesn't explain the neutrino masses, and we already saw that from dimension 5 operators what bounds we can put on the heavy energy scale. So now I'll be discussing, so in the previous Lagrangian I had said that there is only one cutoff scale lambda. So now comes to the motivation. Last day someone else was asking, why do we have one high energy scale, why not two? So here I want to motivate, even in the SMEFT we can very easily motivate two different kinds of scales. So we can motivate lambda L is the scale for odd dimensional operators, example dimension 5 operators which violate the B minus L. So the experimental constraints from neutrino masses, they suggest that lambda L would be of the order of 10 to the power 15. But there is no a priori reason to believe that the theory from which we will eventually get the neutrino masses will be the same theory that would be modifying my weak physics as well. So we can take a completely different energy scale lambda for even dimensional operators like dimension 6 or 8, and this scale may be much lower, could be almost reachable at the Large Hadron Collider or other colliders, possibly in a few TeV range. So we can have access to these kinds of scales at current facilities or in the immediate future experiments. So we assume these hierarchies, V is much less than lambda, and lambda squared is much less than V times lambda L. So these two hierarchies would ensure that the expansion, it converges quickly, and the leading new physics contributions in the weak regime, they come from dimension 6 operators. So here I have written the Lagrangian in a slightly different way. So I have two different scales. Yes.
Like one will be, just go back to the previous slide. Yeah, one will be V by lambda, another will be what, like
lambda squared by V lambda L.
Lambda, so which is a product of the other expansion.
Exactly.
Okay.
So in the neutrino mass slide, suppose you have Dirac neutrinos, then we would need extra right-handed neutrinos to form that.
Exactly.
So in some neutrino mass models also the couplings can be large.
Yeah.
So in that case, are there higher dimensional terms which can be important, or they are always at dimension 5?
for neutrinos, dimension 7 operators would also give corrections.
So del mu H, L.
Yes,
kind
exactly.
of
So
terms
there will be an H dagger H on top of this.
So are they relevant when one has to take into account neutrino oscillations
So
because they are very precise?
They are suppressed by 1 by lambda cube. So they are, so compared to 1 by lambda here, they are suppressed by 1 by lambda cube, so they are much smaller. So unless we can actually motivate why the Wilson coefficient of the dimension 7 terms are going to be much larger than the dimension 5 terms, there is no reason to believe that the dimension 7 terms would dominate. But as you said, if the couplings are large, then we might. So sometimes we see that dimension 8 effects could be as large as dimension 6 effects, and we may not be able to drop them. So there are studies where they have considered dimension 7 effects for neutrino masses.
Okay, and one more thing in the 2 scale slide, suppose you the UV physics which generates your dimension 6 operators, they also contribute to dimension 5. And
Right.
there are some operators which have this lambda L. So in that case, how does one treat these things?
So yeah, so I haven't thought about this. So you're saying that like the same physics which gives dimension 6 operators would also give dimension 5 operators. So we would have to accept that there are contributions to the neutrino mass term from the very high cutoff scenario where we have 10 to the power 15 lambda as well as a TeV region. So there are multiple sources through which the neutrino gets its mass. There's no reason why it can't. Like we shouldn't be biasing ourselves, but yeah, that's the.
Okay, thank you.
Here the lambda L is also much smaller than much greater than nu.
Sorry.
The lambda, what is
it's
the?
V. It's the vacuum expectation value.
Yeah, V. So the lambda L is also much greater than V.
V is 246 GeV, and I said lambda L is 10 to the power 15 GeV. So the LSM is the standard model Lagrangian. Each operator is gauge invariant, as we know, under the combination of standard model fields with the canonical dimension. The Wilson coefficients are all dimensionless, and these are interpreted as the characteristic mass scales. So now to motivate you the importance of dimension 6 operators to characterize low energy effects of heavy particles. This has been known since quite some time. So very recently a complete non-redundant set of operators has been derived, and there are around 2499 operators at dimension 6 if we assume that there is no flavor universality. So there are so many different higher dimensional operators which may yield identical S matrix elements if they are, so I said this before, they are related by equations of motions, if they can be removed by integration by parts, by field redefinitions, or by Fiat's transformations. So if we remove these redundant operators, this would simplify the EFT description, and we will get an unambiguous map from observables to EFT Wilson coefficients. So there are two popular choices at dimension 6, the studies that we do are the Warsaw basis and the Silch basis, but there are many other bases which are often used. So construction of a basis, I already explained that through an example. So starting from all dimension 6 operators, starting from all distinct dimension 6 operators, these could be constructed from all the standard model fields. Many of these become redundant because they are linear combinations of each other. So a complete basis of one generation was constructed just some years ago, and then it was changed, it was modified to 3 generations, and in the Warsaw basis there are 2499 operators. So the number of operators is also basis dependent, it is not a basis independent quantity. The redundant operators can be removed, as I said, and more systematic methods, I do not think I will be able to discuss this because I will not have time, by the Hilbert series techniques can be used to construct the basis. So this is the Warsaw basis operators in, just wanted to flash. So these are the different kinds of operators. So we have the bosonic operators which comprise only the bosonic fields, the Higgs field, the B fields, the W fields and the gluon fields, and also the CP odd fields, and then the field strength tensors, and then we have the 4 Fermi operators. So these are all the different kinds of 4 Fermi operators, and then we have the two fermion operators where we have the Yukawa kind of operators where we have the Higgs and we have the fermions, we have the vertex kind of operators, and then we have the dipole kind of operators. So these are the various kinds of operators at dimension 6 which come about in the Warsaw basis. Yeah, so this is a technique through which the bases are actually constructed. This is like a 5-lecture thing. So yeah, so through path integral formulation we can actually construct a Hilbert series, and we can actually find the basis of not only the basis, the number of operators at every mass dimension we can calculate. So this has been calculated by Hitoshi Murayama, Tom Melia and others. So yeah. So in the 2 fermion case, we have noted that there are, so this is the 2 fermion case, so we have the indices I and j, these are the flavor indices, and for complex operators like the OHUD operator, which is basically here, the Yukawa operators, these ones, and the dipole operators, the complex conjugate is implicitly included, and for the 4 Fermi operators, again flavor indices are there but they are suppressed, and we have these factors eta written as half when we have identical indices like 1 1 1 1. Otherwise eta, when these are not all identical, eta is equal to 1, and these complex operators, they will include their conjugates in the Lagrangian with complex Wilson coefficients. These are the dipole operators. Sorry?
Why the name?
So these actually contribute to, like, for example, some dipole moments as well.
Actually, I can't see, so you probably have to tell me what that is.
So this is basically, you can see this is one EIC sigma mu nu H dagger sigma I LJ W mu nu.
Okay, so this is the okay, this is the Higgs coupling to the E and the L. Of
E and EL and a gauge boson field.
Why is it called a dipole?
So this contributes to the dipole moments as well. So if you compute the dipole moments, these operators contribute. Also, for example, it contributes to an effective vertex like gluon. Like when you compute the gluon to Higgs, these dipole operators also come into existence. So construction of a basis, I have, how much time do I have? I have only 2 minutes. So we basically, if we write down this operator OHD prime as H dagger H d mu H dagger d mu H, what we can do is we can take all the classical equations of motions of the Higgs here, which I have listed down, and we can integrate by parts, and what we get is OHD prime can be written down in terms of H dagger H box H dagger H minus this quantity, and then if we apply the equations of motion, we will be able to say that box of H dagger H goes to minus of mu H squared H dagger H plus 2 lambda H dagger H whole squared. So this operator OHD prime basically becomes this mass term H dagger H squared, and then we have all of these other operators. So if we go back, so it's very small for instance, but if we go back, all of these operators H dagger H box H dagger H, so H dagger H box H dagger H dagger H whole cube, all of these operators are there in the Warsaw basis. So this operator can be traded off for all these operators in the Warsaw basis, rendering this redundant. So I just want to give an example, and I can stop now. So if we take the dimension 6 operators as a prop to parameterize the effects of the BSM particles on weak scale observables. So suppose one day we get to know that a linear combination of higher dimensional operators must be present in the SMEFT. So all experimental results, so we were discussing it the other day, all experimental results point us in the direction of certain operators. So different operators would give us different kinds of physics interpretations, and certain operators, say like after collecting a lot of data, we are able to say that these experimental results point us to a linear combination of higher dimensional operators. So this is the direction of new physics that is favored by this, by the data. So what will this tell us about new physics? So, and then like what we have to do is we have to toil hard, we have to take a lot of theories and we have to see which of these theories actually give rise to that linear combination of operators. So here I have taken a Fermi-like scenario. So I have taken a neutral vector boson V mu with a mass of mv and I have coupled it to the standard model fermionic currents. Again I have written it in the two component notation V mu Gx Fl F bar sigma mu F and Gx Fr. So this is the left handed and the right handed part, Fc sigma mu Fc bar. So for energies which are well below the mv, the momentum dependence in the V propagator can be completely ignored and this would give us this contact interaction like this. So we have 1 by 2 mv squared and then we have again 4 fermion operators. So this is F bar sigma bar mu F and there is a whole squared here. So we will get 4 fermion operators. So if experimental data requires the presence of certain dimension 6 operators in the SMEFT, this will actually provide indirect evidence for heavy particles. So what from here what we will have is that the Wilson coefficients in this case C by lambda squared, they will be proportional to the ratio of the BSM couplings and the masses and this can be used to set an upper limit on this quantity C by lambda squared. So we will not be able to say anything separately for C or lambda, but we will be able to put bounds on C by lambda squared. So experiments will only be probing C by lambda squared and the upper limit on lambda would come from the fact that these couplings cannot be larger than 4 pi. So that is the upper limit that we will be getting. So shall I stop? So after this I have a more realistic example, but we can stop here.
Sorry, I did not follow properly. So when you are setting this lambda L in 10 to the power 15, how do you set that?
I told this, this is how I do it. So V squared by 2m, so how do we write a mass term? So what is the dimension of this V squared by 2 lambda? It's mass,
No,
right?
this is fine. I think in the next slide, lambda L where you are setting 10 to the power 15.
So here I say that lambda by C5 greater than 10 to the power 15. Is this part clear?
I can equate lambda and C5 equally and make lambda something very less than 10 to the power 15.
That's what I said. Usually we can only guess up to lambda, C by lambda. That's the only thing that we can know for sure. But in order to have an idea about lambda, we need to put some assumption about C. So in standard model, what kind of couplings do we have? What is the value of the weak coupling? Around 0.65? Yeah. So if we assume that we have a weak like coupling, then C would be of the order of 1. So if we plug C is equal to 1 here, we will be getting lambda greater than 10 to the power 15. So it's just an assumption that we have a weak theory for the neutrinos as well, at a very high scale.
So when we integrate the field, we can also consider that some large number may come inside the C also.
Yes, but it cannot be larger than 4 pi.
How do you know that actually?
So then like it would break the strong coupling regime as well. Like we cannot.
So I can decompose it, let's say some gauge coupling and some stuff which is coming from the integrated out.
So here what I am saying is that it satisfies the standard model gauge symmetry. The operators, all the operators they have to abide by the standard model gauge symmetry.
No, the C is not only the gauge coupling; it has some.
It has the information of the new physics. Yeah.
New physics also.
Yes.
So when you are integrating some heavy field, how do I confirm that some heavy number is not inside the C5 along with the gauge coupling?
So we are not sure about that because it's a bottom up approach, right? From the bottom up approach we can never be sure. From a bottom up approach we can only say that the coupling C, they must respect that they should be less than 4 pi. It's a perturbative cutoff.
Perturbative with respect to the gauge coupling.
every coupling. You cannot just write it like in this linear sum.
We may discuss later. I'm not convinced actually.
So here you said that this dimension 5 operator, these contribute to the mass terms of the neutrino.
Yes.
So any higher order, higher dimensional operator also can contribute.
As Juhi was saying,
Yes.
dimension 7 operator can contribute to the mass of the neutrino as well.
So here you get the bound of this lambda by C5
Yeah.
from only this operator.
Exactly, exactly. So what will happen is that if I have a dimension 7 operator, so I'll be able to write it as, say, H dagger H times epsilon ij H L epsilon ij H L. Right, so this is what I write, and then from here I get the mass, and from here what I can get is, we'll get after spontaneous symmetry breaking, we'll also get a V squared times this mass. So we'll get a V squared by, in that case it would be lambda cube. So V squared by lambda cube some C prime and the mass term of the neutrino. So this would be there. It's an additional term.
Yes, so the C5, that value could change, that bound could change, right?
That would change, but the thing is that because we are assuming that, we are not just assuming, we are getting this bound on lambda L to be so big. You can assume that instead of 1 by lambda, this has become 1 by lambda cube. So it would be suppressed by a factor of 1 by 10 to the power 30. So it would be a tiny deviation, but it would be there. Vaibhav has a question, and then.
Yeah, in the slide where you showed the Higgs equation of motions.
Oh, sorry. Oh no, it's after. Yeah.
I have the same doubt again, that if a priori you don't know which operator is redundant, how will you write the Lagrangian that will give you the equation of motion?
So, yeah, that's a good question. So we, in fact, we can write all these. I haven't thought about it like that. So the question is that he's asking is that, like, before knowing that this operator is redundant, by using the equation of motion and integration by parts, how am I sure that I am not writing this in the original EFT Lagrangian? Like when I construct my equations of motion, I take my EFT Lagrangian, I do the integration of by parts, and I get these equations of motions. So what he is asking is that, why is it not there? So as you can see here, all the 1 over m, like order m to the power minus 2 terms are not there. So it's basically only the standard model fields which are there. So there are no EFT coefficients. So these are not what I can say for now, that these will not be exact equalities, but they will all have a 1 over m squared suppression with these coefficients, and they will be the deformations to these equations of motions. Vaibhav has a question.
Yeah. Could you go to slide number 37?
Yeah.
So actually, I don't understand how this equation of motion and integration by parts, high dimensional operator are different. So could you give one example which we can have by equation of motion but not integration by parts?
Yes. So here in this toy example that I showed you before, here for instance, these two operators, phi squared box phi squared and phi squared del mu phi, they can be rendered redundant by just using integration by parts. But if you do integration by parts on these two, you will not be able to get rid of them. So to get rid of these two, you need the equations of motion. So that's why there are two classes not all operators are gotten rid of by integration of by parts, not all can be removed by equations of motion, and there are some operators which we will not be able to remove by either of them. So for that we have two other classes of transformations. One is the field redefinition and the other is the Fiat's identity, the Fiat's transformation.
But this classical equation of motion, doesn't it use integration by parts itself? So
yes, it uses the integration by parts in the Lagrangian, but so that's why this only, so you see that I have not included, to answer your question again, order m to the power minus 2. So this from basis to basis, this might change for every single basis, this part might change, but it is suppressed by 1 by m squared. Someone had a question?
Yeah, so you are talking about that SMFT is a bottom-up approach. So in top-down, what happens is we know full theory.
Yeah.
And we know all the interactions.
Yeah.
So it is easier for us to calculate the remove the divergences also.
Yeah.
But in the bottom-up, we don't know all the interactions.
Yeah.
So in that case, how will remove the divergences?
So EFT is not a renormalizable theory, because in EFT there are infinite number of terms and we can only observe finite number of divergences, right? We cannot have infinite number of counter terms. So EFTs are only renormalizable at a fixed order. So when we talk about dimension 5, there is one operator. When we are talking about dimension 6, there is 2499 operators and so on, and then we can renormalize them fully. So that is a valid EFT, but when we take, that is a renormalizable EFT. If we add all the dimensions, then it no longer remains renormalizable. So it has to be renormalized order by order, mass dimension by mass dimension. Yeah.
Do a renormalization calculation in the sense of counter terming.
Yeah.
If you do it at say one loop order, you might generate six dimensional.
Exactly. So and that needs to be, so a higher order operator terms might be needed in order to cancel everything. Yeah. Oh, I think, yeah. Okay, let me, where was this? So the assumption behind that is that one of the neutrino masses is of the order of 0.06 electron volts. That is how I am getting this 10 to the power 15. And then by plugging V is equal to 246 GeV.